Many problems that a computer scientist has to solve involve optimization. These are the client's optimization problems. So a trucking company may need to minimize the cost of their trucks coming to a bunch of different cities. Or a mathematician may need to multiply matrices in a time as fast as possible. In each of these examples, a sequence of choices have to be made in order to arrive at this optimal solution. And then frequently are certain constraints that have to be met. For example, no truck can go to more than some number of places in a given day. There are two common techniques for writing effective algorithms, well-performing, efficient algorithms for solving such optimization problems. One of them is called dynamic programming. It optimizes the overall objective. And then there's greedy algorithms, where the idea is to optimize each step as you go along. We'll talk about both of them in this course, but now we're talking about the dynamic programming solution. Two kinds of problems that are suitable for the dynamic programming approach. One has to do with problems where you have to divide the problem, and there's many choices in how to divide the problem. In the other type of problem, the solution involves a sequence of steps, and at each step you have to make a decision. Let me give you some examples of each of these. In regard to the succession of ways to divide the problem, consider multiplying n matrices together, A1 times A2 times A3, and so on up to AN. Well, you can parenthesize their multiplication. So if you can, for example, compute A2 A3 times A4 and multiply it on the left by A1, or you can compute A1 times A2 and multiply and then compute A3 times A4 and multiply the two results together. Or we can take A1 times A2 times A3, multiply them together, and then multiply the result times A4. Of course, in each of these examples, when you have three matrices to multiply, or two in one of these subgroups, you have to decide also how to parenthesize them. So, for example, in the first situation, the A2 times A3 times A4 has to be, you have to decide whether you're going to multiply A2 times A3 and then multiply the result by A4, or multiply A3 times A4 and multiply the result on the left by A2. So that was an example of a problem that you had to figure out how to divide it. Another example is you have a convex polygon, such as the one you see here on the right, and you want to divide it into triangles. Well, there are very, very many ways to divide it into triangles. one of the many ways is shown in the example. And of the many ways to divide it into triangles, you would like the collection of triangles to have minimum total perimeter. And so the idea is that we start off with the overall polygon with the vertices shown as heavy dots, and you make a decision for the first line from one of the dots to another of the dots, dividing that polygon into two subpolygons. Then, for each of those subpolygons, you need to decide how to divide it, unless one of those polygons is already a triangle. So again, the problem is how to divide the polygons into triangles in such a way as to minimize this objective function, which is the minimum total perimeter. In the first problem, the objective function was computation time. That is to say, how many total multiplies of scalars you had to do to produce the result. A third example of the division problem is you have a big long rod, and you can make it into various size pieces. Ultimately, for every piece size, you know how much you could sell that for. So you could sell a size 3 piece. Let's say everything is in centimeters, so you could sell a 3-inch piece for such and such an amount, a 5-inch piece for such and such amount, a 10-inch piece for such and such an amount, and for every possible size in inches, you want to you know how much you could sell it for, and you want to cut the rod into pieces in such a way that the sum of the selling prices, that's your income, is as great as possible. Here again, the problem involves subdivision. You want to first divide the rod into, at some point, into 2 pieces, one of some number of inches and the other of the complement of the size of the rod number of inches. And then you need to subdivide each one of them until you want to stop, leave a particular piece of the present size, or until it's 1 inch wide and you can't cut it anymore. So these are the problem type of dividing some problem one division at a time, not necessarily into equal subdivisions, in such a way, and to do that successively in such a way that the result at the end optimizes some objective function. The other kind of problem that dynamic programming is suitable for is a problem where you have a sequence of steps that you know you need to make. But at every step, you have some options that you can choose among. So in the top example, you have 2 parallel assembly lines, and you know how long. Okay, sorry. In each line, you have the ability to accomplish a particular task. So you need to accomplish task 1 first, and then task 2, and then task 3, and then task 4, up to some large number n of tasks. But at each stage, for each task, you have a choice of whether you do that on assembly line 1 or assembly line 2. So assume that you have times that it takes to accomplish that particular task on each line. So for task 1, you know how much time it would take on assembly line 1, how much time it would take on assembly line 2. Likewise for task 2. Moreover, you can switch assembly lines at any point that you want, except that it takes time to switch, and you have the switch time recorded. And now what you want to do is you want to produce these devices that you're making on this assembly line in a way that minimizes the time. Another example of a place where you have a sequence of steps. Consider the situation in the lower figure. You have a polygon on the top surface, you know its nodes, and you have a polygon in the bottom surface, you know not necessarily the same number of points on it, and they are in parallel planes, and what you want to do is divide the boundary, to tile the boundary between them with triangles. Every triangle will have one side connecting two vertices on one polygon and one vertex on the other, but it can be in either direction. And say somebody gives you an initial starting connection, a line saying that one particular point will connect to the other. So now the idea is that you need to march around the polygon, making triangles until you come back. And at every stage, if you have a triangle that you've just put in place, a line that you've just put in place, you can either move along the top polygon, leaving the bottom point fixed, or you can move along the bottom one. That's the choice you have to make. And what you want is to choose that particular set of steps that end up with a total, such that the total area of all the triangles is minimum. That's your objective function. So we have, to summarize, we've talked about two different types of problems, and one, how to divide a problem, the other involving how to decide to make each step in a long sequence of steps in such a way as to optimize some global property. These are the two major kinds of problems that dynamic programming is an appropriate solution for. This basic approach for creating algorithms, called dynamic programming, is in fact questionably named. First of all, it doesn't involve programming in the sense that we understand it as. It does not involve coding. Second of all, it's not clear in what sense it's understood to be dynamic. Unfortunately, that's the name it was attached to it, and you'll have to just live with it. But anyway, this approach deals with optimization problems. We've seen examples with many possibilities of how to break them up. And we'll talk about the way in which it should be broken up to get the optimized value, as producing a schedule. So that the solution of the dynamic programming method yields a schedule for breaking up. But the actual application to the problem then has to be accomplished using that schedule. So for example, in the matrix multiplication question, the schedule tells you which matrices you should multiply when, but the actual multiplication of the matrices in that order has to be done by another program that says, okay, as given in the schedule given by dynamic programming, first you multiply this pair of matrices, and then you multiply that pair of matrices, and so on down the line. The other major property of the dynamic programming method in producing the schedule, the production occurs in the opposite order in which it's applied. So the schedule is applied large parts to small. So in the rod cutting example, you have a big long rod, and the first thing you do is cut it into two parts that are also large, albeit smaller than the original. And then you cut those up into yet smaller parts, and so on. So you're going from large parts to smaller parts. But the schedule is worked on in reverse order. So if we have a rod of size 3, of 3 inches long, and we're going to break it into parts that are integer inches, we have two choices. We can divide it into a 1-inch piece followed by a 2-inch piece, or a 2-inch piece by a 1-inch piece. And that decision is dealt with, and then you move on to the 4-inch pieces, which could be broken into a 3-inch piece and a 1-inch piece, or two 2-inch pieces, or left alone. And then you move on to the 5-inch piece. Anyway, the point is you work on the schedule small to large, and then apply the schedule large to small. Let's think about this approach on the chain matrix multiplication problem that we posed. So we will assume that we know the size of the matrices. A1 will be P0 by P1. That is to say, I'll have P0 rows and P1 columns. A2 will have P1 rows and P2 columns. And AN will have Pn minus 1 rows and Pn columns. When you multiply two matrices, the middle one is going to be P by Q, and the other is going to be Q by R. The column count of the first and the row count of the second have to be the same. And we'll see later that to multiply two matrices with those dimensions requires multiplications and associated additions. If that's the basic computational element, a multiplication and addition, it requires P times Q times R multiplications. So just as an example, let's consider a matrix have three matrices, the first of which is 5 by 4, the second of which is 4 by 6, and the third of which is 6 by 2. And so we have two choices of how to divide that. We can multiply A1 times A2, the 5 by 4 times the 4 by 6, incurring 5 times 4 times 6 multiplications. And that produces a 5 by 6 result that then gets multiplied by a 6 by 2, which will take 5 by 6 times 5 times 6 times 2 multiplication and addition pairs. If we add those two products up, you get the total number of multiplication addition pairs, and it's 180. On the other hand, we could multiply A2 times A3 first, which will require 4 times 6 times 2 multiplications. One is 4 by 6, the other is 6 by 2, and produces a 4 by 2 matrix, which we're going to multiply by the 5 by 4 matrix A1, which will produce 5 by 4, 5 times 4 times 2 multiplications. So the total multiplications to multiply the three matrices is 88 multiplication, or more precisely multiplication addition pairs. Even for this small example, considerable savings can be achieved, we see, by reordering the evaluation sequence. One of them takes roughly twice as much work as the other. And if you have a big, long set of matrices, n of them, to multiply, it can be a heck of a big difference between one choice and the other. And so dynamic programming is about choosing this sequence so as to minimize the total number of computational elements that will need to be used when the actual calculation is done. Now let us come back to our rod cutting example. A property of that rod cutting example is that there may be many pieces of any given size, say size 5, that will have to be cut or left alone. And in this problem, whatever is the best cutting procedure for one piece of size 5 is the same as for the other. And so part of the dynamic programming method must keep track of what subschedules we've already computed, so that we won't have to recompute the schedule. The algorithm design paradigm called dynamic programming is similar to divide and conquer in the sense that it breaks down problems into smaller problems that are solved recursively. But in divide and conquer, first of all, the way in which it breaks the problem is decided on some global basis. And secondly, the subproblems in divide and conquer are independently solved. But in dynamic programming, some of these sub-problems may repeat themselves, and we have to save the results in a table to avoid duplicated computation. Summarize what we have said of what the elements of dynamic programming elements are. The basic form is to decompose a problem into smaller subproblems, and then recursively to express the solution of the original problem in terms of solutions for smaller problems. In order to decide what decomposition should apply in a particular situation, we store the answers to the subproblems in a table. Actually, two tables. One which records the costs. That's the table we called M. And one which records the schedule, in both cases for a particular a subproblem of a particular size. These tables are generated small subproblem size to large subproblem size, and as a result, as we get to larger and larger subproblems, we eventually arrive at a solution to the full problem, the problem of the original size. In our rod cutting example, this works as follows. At any given stage, we cut the rod into two pieces of sizes that sum to the present size, but whose specific sizes will need to be decided. And each of those will be will need to be further cut to optimize income, which is the sum over all of the final pieces of the price of that piece size. We may, in this example, have to cut a rod of size 4 many times. Perhaps when we decompose a rod of size 37, both pieces of that rod of size 37 may eventually get down to pieces of size 4. And the bottom-up computation means we need to first figure out how rods of size 2 should be divided. There's really only two choices. Either don't divide it or divide it into two rods of size 1. And then we move up to rods of size 3, which can be left alone or divided into a rod of size 2 and a rod of size 1. And then we move up into a rod of size 4, which can be divided into a size 3 and a size 1 rod, or two size 2 rods, or left uncut, and so on for larger and larger rods. Rod cutting example that we've been using is an instance of the kind of dynamic programming, a kind of problem suitable for dynamic programming called optimized chain operations. We have a chain of operations, and we have to decide in what order to perform them. This general class of problem appears in compiler design for code optimization and in database software for query optimization. So it's really quite important for computer scientists problems as well as for problems that our users need to solve. Besides the rod cutting problem, another example is how to parenthesize the multiplication of matrices to minimize the computation time. We've already said a bit about that, and we'll now give much more detail. And another example, which we will face later, is how to divide a convex polygon into triangles with minimum total perimeter. Our problem is to optimize the time of chain matrix multiplication. This involves choosing the parenthesization, and any parenthesization it's fair to consider because multiplication is associative. Matrix multiplication is. However, we can't reorder adjacent pairs of matrices. If you have a matrix A times a matrix B, it may even not make sense to consider B times A because multiplying A times B requires the column count of A to be the row count of B, which may not be satisfied when you're multiplying B times A. But even if it does make sense, A times B does not give you the same value as B times A. Matrix multiplication is not commutative. So we have to keep the order of the A sub i's. An additional property that we need to understand is that when we multiply a P by Q matrix A times a Q by R matrix B, not only does the number of columns of A, which is Q, be equal to the number of rows of B, which is Q, but the result is a P by R matrix, C equals A times B. If we look at how that works, the formula for the product is the sum over K of AIK times BKJ. So we have Q times around the sum loop, and each one requires a multiplication and an add of an entry in A times an entry in B to produce one of the entries, the ijth entry, in C. But C has PR entries, so we have PR times Q. That is to say, the number of multiplication add combinations to multiply two matrices is P times Q times R. So now consider a sequence of matrices, A1 through AN, the first one of which is P0 by P1, the next one P1 by P2, and the last of them is Pn minus 1 by Pn. Then, if we divide a sequence, A1 through AN, into A1 to AJ, and then AJ plus 1 to AN, the first one is P0 by PJ, the second one is PJ by PN, and so if we had already computed each of those two products, that is to say we had parenthesized into A1 to AJ as one parenthesized expression and the AJ plus 1 to AN, then the cost of that is the cost that it took to multiply out the left side, the A1 through AJ parenthesized expression, plus the cost to multiply out the right side, the AJ plus 1 to AN expression, plus the cost to multiply the two parenthesized expressions, which we have worked out is P0 times PJ times Pn, where the first product is P0 by PJ, the second product is PJ by Pn. Our overall problem for the chain matrix multiplication solution is to determine the multiplication sequence that minimizes the number of operations. This is solved by the dynamic programming approach, which yields that sequence. That is to say, it yields a schedule for the operation. The dynamic programming algorithm figures out the schedule given the P sub I values. So you have to give it the sizes, but you don't give it the actual matrices. After you give it the sizes, the dynamic programming algorithm computes the schedule, and then a separate algorithm performs the multiplication itself, the multiplication of the matrices themselves, given the schedule. Let me remind you what we showed already earlier, that multiplying a 5 by 4, a 4 by 6, and a 6 by 2, there were only two ways to divide it, to parenthesize it, and one of them took 5 times 4 times 6, multiplying the 5 by 4 by the 4 by 6, and then producing a 5 by 6, and then multiplying that 5 by 6 times 6 by 2 to get a total of 180 multiply-adds. Whereas if we broke it up the other way, we first multiply the 4 by 6 by the 6 by 2, A2 by A3, getting something 4 times 6 times 2 multiply-adds. And then we multiply the original 5 by 4 by that 4 by 2 to get that costs 5 times 4 times 2, and thus the total number of multiplications is 88. This example, I repeat, is to show you that it can matter. So how can we figure out a best schedule? Naively, we could consider all possible parenthesizations and evaluate the cost of each and find the one that produces minimum cost. How much time would this naive approach take? Well, if there was just one item, there's only one way to parenthesize it. There's no parenthesization. If we have n items, there are n-1 places where you could break the list. Namely, after the first item, after the second item, and so on, up to after the n-1th item. Having split after, say, the kth item, we create two sublists, each of which has to be parenthesized, and one of them has k items and the other n-k items. And then we have to consider all ways to parenthesize those. If there are capital L ways to parenthesize the left sublist, and capital R ways to parenthesize the right sublist, the total number of possibilities is L times R. Given the results of the previous slide, we can now consider how many different ways are there of parenthesizing n items. We would need to evaluate each of them with the naive algorithm. So there's only one way to parenthesize one item. And for n items, the number of ways to parenthesize it is the sum over all breakpoints of the number of ways to parenthesize the first sublist times the number of elements in the second sublist. This P of n formula is solved by an analysis called Catalan numbers, which are omega over 4 to the n over n to the 3 halves in required number. The n to the 3 halves, of course, is negligible compared to the 4 to the n. So the number of ways to choose these parenthesizations is exponential in the number of matrices to be multiplied. Completely unusable. We need a better way of doing it. We need a solution which runs in polynomial time. And for this problem, we will prove later that the dynamic programming solution is of polynomial order. I should mention now that there exist problems to which the dynamic programming approach is applicable, but which nevertheless produces solutions that aren't of polynomial order. That is to say, that they're of exponential order in performance time. Let's work on this particular problem. First of all, let's define a notation, A sub I dot 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 J, to be the product of the matrices AI through AJ. This matrix, A sub I dot 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 J, is a matrix with P sub I minus 1 rows and P sub J columns. We're multiplying two matrices together to form A1 dot 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 n, or in general for AI dot dot J. At the highest level, say we have A1 dot 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 n is going to be broken up between the kth and the k plus 1th matrices so that it's A1 dot 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 k times a k plus 1 dot 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 n. And of course the question is what k is going to be best for us. So we need to consider all possible values of k and choose the one which is going to give us the least time. Once we have A1 dot 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 k and a k plus 1 dot 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 n, that once we've chosen k, we need to recursively apply our cost minimization to the respective matrices forming this product. But we will need to build the table of the k choices not from largest to smallest, that is to say, not beginning with A1 dot 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 n, but from smallest to largest. So we'll talk about splitting small chains and then yet larger chains and yet larger chains. More specifically, we'll start since we know how to split this one matrix, is no split, and two, the split is completely clear. So the first one of importance is how to split a group of three matrices, which could be split after the first or after the second. And then we'll move up to chains of size 4 and chains of size 5 and so on. And as we produce these solutions, we will put the result in a table that eventually will allow us to give the full solution and will produce the overall schedule that we can then apply to the actual multiplication. So we will be computing a value m sub ij, which is the minimum number of multiplications needed to compute the matrix A sub I dot 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 j. So in this example where n equals 9, that is to say we're multiplying 9 matrices together, we will be interested, for example, in m of 3, 7, that is to say the minimum number to compute the product of A3 through A7. So you should work out for yourself, in terms of the P sub I, what is the dimension of the matrix A sub 3 dot dot 7? And also, if we have this matrix A3 dot 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 7 and want to split that product of 5 matrices between A5 and A6, how many multiply add pairs will that particular multiplication of A3, A4, A5 times the A6 dot 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 7, how many will that require? The matrix that is the product of A3 dot 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 7 has dimensions P2 by P7. That is to say P sub the first index minus 1, that's 2, 3 minus 1, by P the last index. And so A3 dot 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 7 has the, when it's split into A3 dot 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 5 and A6 dot 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 7, that first triple of matrices is P2 by P5, and the other one is A6 dot 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 7 is P5 by P7, and therefore that multiplication requires P2 times P5 times P7 multiply add pairs. We need an algorithm for computing the cost m sub ij, that is to say, the best way, the least cost, where we can divide the matrix A sub I dot 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 j to produce the matrix multiplication. We can explain this cost by saying that for A sub I dot 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 j, if I equals j, that is to say there's a single matrix, the cost is 0. But if j is greater than I, we have to consider each split point and minimize over the costs. The equation at the bottom, the two equations at the bottom express that. M sub I equals 0, and M sub ij, the cost for evaluating the matrix A sub I dot 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 j, is the minimum over all breakpoints k of the expression for cost that we have previously discussed, namely the cost for computing A sub I dot dot k, the cost plus the cost for computing A sub k plus 1 dot dot j, plus the multiplication cost, multiplication and add cost, to multiply these A sub I dot 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 k with A sub k plus 1 dot 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 j. Repeating, if we split after a particular k, then computing A sub I dot 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 k takes M sub I k multiplication and adds. The rightmost factor, A sub k plus 1 dot 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 j, requires M sub k plus 1 comma j multiplications and adds. And thus the calculation of A sub I dot 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 j with a split at k, in addition, requires the time to multiply A sub I dot 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 k times A sub k plus 1 dot 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 j, which requires P sub I minus 1 times pk times pj multiplication and adds, because A sub I dot 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 k is P sub I minus 1 by pk, and A sub k plus 1 dot 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 j is pk by pj. Then, knowing that the break at k requires M sub I k plus M sub k plus 1j plus P sub I minus 1 times pk pj multiplications and adds, we now need to compute M sub ij, which is the minimum over all breakpoints of that value. We evaluate the parenthesized expression for all k and minimize. Note that the entries in the expression being minimized involves shorter sequences, I to k and k plus 1 to j, than I sub j. And if we are building these things small sequences to large, we already have values of M sub ik and M sub k plus 1j that we need in computing the minimum value M sub ij. Of course, the ultimate objective is not to compute the minimum cost, but rather to compute the schedule that we will use for breaking up the large chain of matrices into parenthesized expressions. And so when we find that a particular Mij yields a breakpoint k that minimizes that cost, we need to record that breakpoint. So we're going to create another table, S of ij, which is the schedule matrix. And that says if we end up with a matrix A sub I dot 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 j, then our breakpoint will be at position S sub ij. In mathematical terms, S sub ij is the argmin over all possible breakpoints of the cost expression we've previously seen. You need to be familiar with the mathematical notation argmin and argmax. Whereas min of some expression gives the smallest possible value for that expression, argmin gives the argument that produces that minimum. In this particular case, it gives the value of k that yields the minimum cost. Extracting the optimum sequence, we're maintaining two arrays, one for the minimum values of m when it's applied to the matrix A sub I dot 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 j, that is to say m of ij is that value, and the other one being the split marker, that is to say the value of k that provides that. So intuitively, Sij tells us what multiplication to perform last. We only need to store S sub ij if we have two matrices and j is greater than I. Let's look at an example to solidify our understanding of this algorithm. Here we want to multiply a 5 by 4 matrix times a 4 by 6 times a 6 by 2 times a 2 by 7. To begin, we write down the four basic matrices, A sub 1, A sub 2, A sub 3, A sub 4, along the bottom of below the M array that we're going to produce. And straddling each one of them are its row and column sizes. So A1 is straddled by 5 by 4, A2 4 by 6, A3 6 by 2, and A4 2 by 7. The very bottom row of the M array, the one with all the zeros in it, have zeros because they represent the cost of computing a single matrix. There's no multiplications there at all, so the cost is 0 for computing A1, similarly 0 for computing A2, and so on for A3 and A4 respectively. The next row up involves calculating A1 dot dot 2, that appears in the leftmost position in the second row from the bottom. A2 dot dot 3, whose M value appears in the middle position, and A3 dot dot 4, whose M value appears in the rightmost of that row. It's very straightforward to compute those because there's no breakpoint and because the constituent matrices are all singlets which have no cost as recorded in the first in the bottommost row, which we've already computed. So the cost for A1 dot dot 2 is 0 plus 0, the cost for A1 and the cost for A2, plus 5 times 4 times 6, because we're multiplying a 5 by 4 times a 4 by 6. And 5 times 4 times 6 is 120. Similarly, to get A2 dot dot 3, all there is 4 times 6 times 2, or if you will, 0 plus 0 plus 4 times 6 times 2, which is 48. And finally, for A3 dot dot 4, the result is 6 times 2 times 7, strictly 0 plus 0 plus that product. And 6 times 2 times 7 is 84. And so the second row was easy because there were no choices of breakpoints. The third row from the bottom, however, involves the calculation of three matrices, namely for the leftmost A1 dot dot 3 and for the rightmost A2 dot dot 4. Now there are, for each one of those, there are two choices of breakpoints. Let's consider the calculation of A1 dot dot 3, whose result appears in the slot filled in with 88. The two choices are to break after 1 and get A1 times A2 dot dot 3, or to break after 2 and get A1 dot dot 2 times A3. In the first case, we have the cost for A1, which was recorded in the bottom row as 0, the cost plus the cost for A2 dot dot 3, which is the 48 in the middle row, element of the second row from the bottom of the M array, plus the cost of multiplying these two matrices, A1 and A2 dot dot 3, times each other. A1 is a 5 by 4, A2 dot dot 3 is a 4 by 2, so the cost is 5 times 4 times 2, and the total cost, if we broke after 1, would be 0 plus 48 plus 40 is 88. But we have another choice for computing A1 dot dot 3, and that is to break after 2. In that case, we're multiplying A1 dot dot 2, which has a cost recorded as 120, the first element in the second row up from the bottom, plus the cost for A3, which is 0, plus the multiplication cost, and since we're multiplying a 5 by 6 times a 6 by 2 gives us 60, plus 120 gives us 180, which is greater than 88, and so we choose the 88. That is to say, we choose the breakpoint to be after A1. The value 104 is analyzed similarly in regard to computing the matrix A2 dot dot 4, which can be broken after 2 or broken after 3. Again, there's two choices. We compute both of them in the way similar to what we saw for the A1 dot dot 3 that we've already shown, and the answer turns out to be 104. Having computed the three bottommost rows of the M matrix, we now move on to the product of matrices involving four matrices, A1 dot dot 4, which is in fact the final result. For that one, we have three choices. We can break after 1, we can break after 2, or we can break after 3. Breaking after 1 corresponds to multiplying A1 times A2 dot dot 4. Breaking after 2 corresponds to multiplying A1 dot dot 2 times A3 dot dot 4. And breaking after 3 involves multiplying A1 dot dot 3 times A4. Let's analyze these one by one. Breaking after 1 involves first A1, which is a basic matrix. Its result is in the bottommost row, its M result. That's 0. And then A2 dot dot 4 is the 104 in the rightmost element on the row corresponding to multiplying three matrices together. So we get 104 into that slot, and then because we're multiplying a 5 by 4 matrix A1 times a 4 by 7 matrix A2.4, the additional cost is 5 times 4 times 7. That's 140 added to 104 gives 244. We'll see in a moment that one of the other two choices gives a lesser total cost than that. So now we consider breaking after A2, which is A1.2 times A3.4. A1.2 is something involving two basic matrices. It appears thus in the second row from the bottom and has the M value of 120. A3.4 likewise has the value 84 from that same row, but on the right side. And we're multiplying a 5 by 6 times a 6 by 7, which gives us 210 plus 84 plus 120, which is, again, a value that's pretty large as compared to what we will see in the very next element. The final choice was A1.3 times A4, breaking after the third matrix, in which case we have A1.3, which involved three matrices. Its result is in the third row up, namely the one with 3 next to it along the diagonal on the left, and the value is 88. A4 is a basic matrix. Its entry is the last in the bottom row, which is 0. There's M value is 0. We're multiplying a 5 by 2 times a 2 by 7. That gives us 70 plus 88 is 158, which is the smallest of the three that we've choices. So we choose the minimum with 158, and we say we should break after A3, thus recording a 3 in the S array. Looking at the S array, the array of recorded breakpoints, we saw that in multiplying A1 times A2 to produce A1.2, there's only one possible breakpoint after 1, and that's the one in the lower left. Similarly, for A2.3, the breakpoint was after 2, and for A3.4, it was 3, and thus we see 1, 2, 3 along the bottom of the S, the breakpoint array. Moving up to the next row, to compute the 88, we had concluded that we needed a breakpoint after 1, which is recorded in the leftmost position on the second row, the one corresponding to A1.3. And the breakpoint for A2.4 we didn't actually compute in the previous slide, but it turns out to be after 3. That is to say, we wanted to multiply A2.3 times A4, and so we record a 3 in that position. Going to the top, we concluded that we wanted to get the breakpoint after 3. We wanted to multiply A1.3 times A4, and so the breakpoint after 3 is recorded as a 3 in the topmost position in the S array. What that means is, going from top to bottom now in application, we first do a breakpoint after 3, which means multiplying what's coming with A4. What's coming is A1.3, and so we move down to the left to see what we do with that one. Had we moved down to the right, we would have seen another breakpoint. Had we broken not after 3, but after, for example, 2, then we would have had to use where to break the A3.4 a array, and then that would have been the 3 that we've recorded on the second row on the right. But we actually didn't use that because we concluded to break after 3, which means we need A1 dot dot 3. And A1 dot dot 3's position is the first one on the second row. And that one says to break after 1. That is to say, we want A1 times A2 dot dot 3, and then A2 dot dot 3 as a trivial breakpoint after 2. The result is the computation tree that we see below, or alternatively the parenthesization that we see at the bottom, which says multiply this big parenthesized expression outermost on the left times A4, and then within that multiply A1 times the parenthesized expression A2 times A3. Overall algorithm. We initialize all our m sub I scores to 0. And then we go over all start points, so over all lengths of subchains from bottom to top, 2, 3, 4, up to n. And then inside that, we iterate over all start points of the subchain of that length, calculate the endpoint, do a minimization, which runs over the breakpoint possibilities, and find the minimum. Each time we find a minimum, we record that breakpoint, and as the minimum gets smaller and smaller, the breakpoints keeps getting replaced. So we finally have the M array and the S array. Now if we look at what's going on here, in steps 2 to 3 we have a loop of length n, so that takes theta of n time. In the loop starting at 4, there are 3 loops, one inside the other. The for loop at 4, the do for loop at 5, the do the for loop at 8. So there are 3 nested loops. So that's going to be what contributes the most. It's the first outer loop has n-1 possibilities, and so on. Let's be more careful about that on the next slide. We've seen that the Sij is used to extract the actual sequence, and we compute S and M. There are 3 nested loops, and each can iterate on the average order n times, so the total running time is theta of n cubed. Another way of looking at it is we're looping over the S and M entries, of which there are n squared over 2 each. And for each, we're looping over the subchains that are theta of the length of the row, which for most rows are order of n long. And so, again, you get theta of n cubed time for this algorithm. Obviously, way faster than the exponential that resulted from the naive approach. Of course, we still haven't multiplied our matrices. Given the values of the P sub I, we've computed the S array, which is used to compute to multiply the matrices. Multiply the matrices is a recursive application, large size to small size, of the schedule array. That is to say, assuming we have to do a multiplication at all, j is greater than I, we compute the split point. Initially, j is n and I is 1. We multiply the matrix a sub I dot dot k with a sub k plus 1 dot dot j. But of course that calls recursively the mult function, each with its own split point, and we're done. How we found the solution to a chain problem. First, we had to figure out what choice we have to make at each stage. The choice is where to split the list of matrices. At each stage, there are a number of options, and we'll list those. Each of those options requires smaller subproblems to be solved. And so if we work small problems to large in an iterative fashion, we can iteratively minimize the cost and in the process produce the schedule. Given the schedule, we use a recursive function with that schedule to designate which subproblems we will actually compute with, and that schedule provides the minimum work over all the options that we had to make. We are done with this video lecture, which takes on the order of an hour and 15 minutes. We'll move on to a second lecture where we will deal with more examples of the type of problem we've dealt with so far, but which yield additional complications, and then move on to solving the other type of problem that we said dynamic programming is appropriate for. But before we move on to the other lecture, you should answer the questions on this worksheet. I have 2 exercises for you to do, which will be done in inverted fashion. The first is for you to solve a matrix chain multiplication problem. Your result needs to be the cost array M and the schedule S. And the second exercise is for you to solve the rod cutting problem, which is also a question of where to divide. So here again, you need to create both the cost array M and the schedule S.